Hi, in this video I'm going to discuss the acidity and basicity of cations and anions in a solution. So salts can be acidic, basic, or neutral when dissolved in solution. So the solutions that they form when they dissolve can be either acidic, basic, or neutral. And that's going to depend on what your anion is, what your cation is, and then what the relative strength of those are. So I'm going to start with the cations first. So alkali metals and the heavier alkaline, so that would be, calcium, strontium, or barium, are non-acidic, right? Meaning they don't react with water. On the other hand, small metals with large charge do react with water. And that makes them acidic. So an example of these would be iron 3+, aluminum 3+, zinc 2+, chromium 3+, and there's other ones, but those are examples of smaller cations that have a fairly high charge. Now what happens is the positive charge on the cation, on the metal, attracts the oxygens in water molecules. So you get what's called hydration to occur. So if I have iron 3 here, right, it attracts actually 6 water molecules around it. So now it's coordinated to those 6 oxygens. And since the oxygen is now bound to the iron, it weakens the bond between an oxygen and a hydrogen. So if I were to write what the formula of this one down here is, it's iron H2O 6 3+. Right? Because water doesn't have a charge, so the charge is still what the charge of the iron is. Alright, so if I have now a water molecule floating around in solution here, which we do since we're in an aqueous solution, because that oxygen-hydrogen bond has been weakened, I can take away one of those hydrogens. And what this gives me now is, I'm not going to write out the whole structure again, but you can see I'm just taking one hydrogen away. So now it's iron H2O 5 OH 2+, right? Because now an OH is negatively charged. But the oxygen is still bonded to the iron, so I'm not getting a hydroxide ion in solution, right? That's critical now. I'm not getting a hydroxide ion in solution. The ion I'm getting is hydronium from right there, right? The water picked up a hydrogen to give you hydronium. So that's how the metals can be acidic. And you'll see in the next video I do about Lewis acids and Lewis bases how the metals are acting in this case as a Lewis acid. Okay, so next up are anions. And for anions, any conjugate base of a strong acid has no basicity. It won't react with water. So this would be NO3 minus, Cl minus, Br minus, I minus, ClO3 minus, ClO4 minus. An exception is bisulfate, so HSO4 minus. Because it has another hydrogen on it, that one's not going to have no basicity. Or no, it has some acidity to it, it has some basicity to it, because it still has an ionizable proton. But the other 6 conjugate bases of a strong acid will not have any basicity in solution. Now that means any conjugate base of a weak acid reacts with water. So it has basicity. So an example here, if I've got NO2 minus plus water, I'll get HNO2 and then OH minus. So I formed hydroxide here, and that's the reason I have a basic solution with the anions. Now, like I mentioned with the bisulfate, right, HSO4 minus, if a weak base has an ionizable proton, determining whether it's going to be acidic or basic has to do with the relative strength of the Ka versus the Kb. So for this, if Ka is greater than Kb, it'll be acidic. And if Kb is greater than Ka, it's going to be basic. So that one, you'll just have to look up the value of the Ka. And remember, if you have Ka, you have Kb, right? So, or you have Kb, you have Ka, because they're related by the Kw equation. Ka times Kb is equal to Kw. Right, so if you have one, you have the other, and you can determine whether it's going to be more acidic or more basic. Okay, so to wrap all this up then, I'm going to discuss what happens if you have a cation and anion together in solution. Because you always have a cation and an anion together. Right? You can't make a solution of just chloride, like Cl minus ions. You can't do that. You have to have, for every negative charge you put in a solution, you got to have a positive charge too. So 1, if the cation and anion do not react with water, solution is neutral. So pH would be 7. An example would be, sodium chloride or rubidium chlorate, right? Barium nitrate. 2, if cation reacts with water and anion does not, solution is acidic. So these would be, like a metal, say aluminum with nitrite, right? Aluminum nitrate, with nitrate. Or iron 3 chloride, right? The anion does not react with water, the cation does. So those would be acidic. 3 is going to be now if the cation does not react with water and anion does. In this case, solution is basic. So this would be, for example, Kf or barium sulfate, calcium carbonate. Then lastly, if both cation and anion react with water, the pH will depend on magnitude of Ka versus Kb. Right, it's kind of like I was talking about with the bisulfate, right, HSO3 minus or HSO4 minus. Right, so an example here would be iron sulfide or zinc fluoride, magnesium sulfate. Right, those are all examples of ones where both the anion and the cation will react with water. So you have to look at the Ka and the Kb of the cation and the anion to see which one is stronger. Alright, so my last video on acids and bases is going to be on Lewis acids and Lewis bases, which is a different definition of them versus the Bronsted-Lowry.